And again, if you want to move your tables around, you may. See if we can get half the tables facing this way and half the tables facing that way. Let it be a psychic experiment for the next group that comes in. All right, now starting material, that's going to show up on the last test. What do you know about magnets? They're charged.
How's the other word?
They don't seem necessarily charged, but they somehow attract and repel depending on the sides.
What are the sides called?
Poles.
Okay, what are the two choices?
Positive.
Typically not called positive and negative.
Now.
Pardon?
North and south.
Yeah, north and south. So I assume that, I think the spirit of what you were saying is right. Now, do magnetic charges exist? We haven't found them yet. Not in the sense like an electric charge. But we talked about north poles and south poles. When we're dealing with electric charge, we've got a positive charge, negative charge. I can have a positive charge sitting in my hand, or I can have a negative charge sitting in my hand. Magnets, on the other hand, if I got a north pole, I got a south pole. I don't have just a north pole or just a south pole. Maybe. So the reason why I'm hedging on that is that there are some physicists who are actively looking to find a north pole by itself or a south pole by itself. Those would be called magnetic monopoles. Now, my understanding of it is that there's still a north pole and a south pole, but I'd have a north pole here, and there'd be a very thin quantum connection with a south pole someplace completely different that is sort of off the screen, but if there's a north pole that exists, there's gotta be a south pole that exists somewhere, and they're somehow connected. But what you would see is just the north pole. Now, if they could find a magnetic monopole, well, probably a Nobel Prize, and there's a lot of the stuff that we're doing is going to change slightly. Theorists have already come up with, here's the set of equations. If they find a magnetic monopole, the math is already in place. We will assume that magnetic monopoles do not exist. But maybe they do. They've just not been found yet. All right, so there's a north pole and a south pole. So if I take a magnet, with a north and a south, what happens if I cut it in half?
Create new north and south poles.
Yeah, they're just smaller. So I'll have a north and a south, and I'll have a north and a south. Now, there are some analogies between what we've done with electricity or with electric stuff and magnetic stuff, using the official terms. And so there are these things called magnetic fields. Magnetic fields, the field lines go out of north and into south, external to the magnet. Internal to the magnet, it's going south to north. So this would be the magnetic field line. That is going the wrong way there, going that way. And you basically draw them until you get tired of drawing them. The symbol for the magnetic field, as you would expect, is B. Why B? My understanding of the history of it is the person who established that had a bunch of vectors he needed to write down, and the first one he labeled as A, the next one was B, the next one was C, and so on. Magnetic field happened to be the second one. If you're looking at some textbooks, they will say that B is not the magnetic field, but the magnetic flux density. Magnetic field, which is what, or flux density. Those who say it's a magnetic flux density say that there's a different thing called H, which is the magnetic field. But the difference between B and H is a constant. So I just put this up here for, in case you happen to run across it. That's more senior level physics and graduate level physics where they do this. So I'm just going to erase it, and we will stick with magnetic field being B like most undergraduate textbooks do. Magnetic fields have units. Anyone happen to know the units of a magnetic field? There's a car named after it. Or maybe they named it after the person, and so are the units.
Tesla?
Yep, the Tesla. Now, if you're looking at older sources, they won't use Tesla as the units. They will use a different one named after a different person. There's also the Gauss. So that's the Tesla. And then there's the Gauss. In the old metric system, the CGS system, Gauss was the preferable one, but in the NKS system, or the international standard, Tesla is the standard.
Is Gauss lowercase g or uppercase G?
The symbol, and that's one of those things that I just, because I was thinking there was a G, it was GA or something like that, but hopefully I have it written down someplace easily found. Nope, just big G. I just realized that there was one prompt that I want to get to give you some evidence that magnetic fields exist. So I'm going to pause this. Why don't we just go ahead and take a small little break here while I go get the prompts. All right, so what we have here are a bunch of little iron rods that are in just whatever random order they are. I guess I put them in the same order there. There's only so much I can do. And so if I take a magnet, and what I have here is just a bunch of little button magnets that I picked up at Lowe's or Home Depot. And you notice that they start to reorient. We have the moving straight in like that. There's also, you get a sense of the curve there. This one seems a little bit off, so the further away you are, the less pull that it will have. Now I can't tell which is the north side and which is the south side, but there does seem to be something happening that is swirling around the magnet. And if I break it in half, again, we get the reorientation, but it's a weaker magnet, and we're also a little bit farther away from it at this point, and so there's less of an attraction there. All right, so now we have a bunch of tiny little iron filings. A little bit clearer. I'm gonna kill the lights with this. So I have a bunch of iron filings that are suspended in some sort of oil. And if I take my magnet, we can start to see that immediately it starts to react to it as the little filings are attracted to it. But you could also see the curves that start to form here with the filings, especially see it along there. It's science, so it's not proof of magnetic field lines, but it does give some sort of credence that there does seem to be something that is going from one end to the other of the magnet. Questions?
Is it, I mean, it seems to be a little weaker in the middle. Is that because the north side and the south side are at the ends? Or?
Yeah, what's external to the magnet is coming out the ends. You can see that it's not, when we're doing a nice board drawing, it nicely comes out of the end like that, but in reality, as you can see, it's coming out of there as well. Did that answer your question?
Yeah.
Other questions? Now, we are going to assume the nice ideal that the magnetic field lines come out the ends. And that's composed of a bunch of tiny magnets. If I take this one right here, that's just a weaker magnet, so that's less impressive. That's also not a particularly strong magnet. And that is a very strong magnet. Although the filings over here is. You definitely see the lines there. All right. I suspect at this point, physics is the only, or the physics instructor is the only ones who still use the overhead projector for that one demonstration. Or if you ever want me to do my dissertation talk, I got a whole bunch of slides for that. Because PowerPoint was only used by the crazy people at that point, chemistry. Go figure. Still going, I hope. Light is blinking. All right. Well, I know what you're thinking. All this is great, but where's the math? We're saying that magnetic fields exist, but how do you actually calculate it? I give you the Biot-Savart. It is spelled like Biot-Savart. one textbook was kind enough to actually talk about how to pronounce it. It rhymes with Leo Bizarre. So Bio-Savar. There are 4 forms of this equation. And they're not, I mean, they're all derived from one of them. So I now give to you the second physics equation of this course. Let's make sure I don't get something in the wrong place. So do not over 4 pi dq v cross r over r cubed. All right, form number 1. This is why Physics 152 has huge disadvantages, because this is really as simple as it gets, and then we use it to derive it. So 152 is more of a, here's the situation, here's the equation, which is painful. But we are fortunate enough that we have calculus, and we can derive things from this. But notice what we have here. 1, as R increases, the farther you get away from it, the weaker the magnetic field is. And well as the key principle, the key thing that creates a magnetic field is I have a charge that is moving. We have a cross product, should bring back some fond memories of cross products. If I have a vector A going this direction and a vector B going that direction, A and B, what is the direction of the cross product? A cross B.
Should be this way.
How'd you get that? Felt right? Benjamin, how'd you get that?
Right hand rule.
Yep, right hand rule. You put your hand in the direction of the first vector, and I got 360 degrees of freedom. I want my fingers to bend so they bend towards the second vector, and my thumb points in the direction of the result. Another way that you can do it, if you think about this, because what we dealt with in 151 or 251 was torque. Torque was R cross F. So if I have a door here, for example, and I apply a force here, it would cause that door to swing counterclockwise, and using the right hand rule for that, counterclockwise rotation would be, the math direction would be out of the board. So A cross B, out of the board. So if I have a charge, let's assume a positive charge, cruising off to the right, and I want to figure out the magnetic field at this point, well, the direction of the magnetic field. Let's not go crazy on the other stuff. R is where the Q is at that moment. So what do we call that one? R, V is to the right. What is the direction of the magnetic field? My R's and V's look a lot alike there. That's it, V. The direction of the magnetic field.
Out.
Yes, out. V cross R puts us outwards. What about down here? So now R is this way.
Into the board.
Yeah. So my magnetic field above, the way I've drawn this, with the charge going to the right, above, the magnetic field is coming out of the board, and down here going into the board. Now I said there are 4 different forms of this. This is one of them. We can derive the other one simply enough. Any questions before I give you the second form of this?
So since this is the second formula, it's completely independent from all the charge stuff,
Yes,
and there's no connection at all?
well, there's charge there. But this is not connected to the electric, this formula is not connected to the electric field at all.
Is that constant?
That?
Yeah.
Is this the first time I guess it is the first time. This right here, because remember epsilon naught was permittivity of free space? This is the permeability of free space. Really would have been nice if they had come up with something that doesn't even sound close, but permeability of free space. If I dropped the subscript there and just had a mu, then it'd be the permeability of whatever the material is, the magnetic field is going through.
So does that mean basically the same thing, just in magnetic field instead of electric field?
Yes. Its value, mu sub naught, is 4 pi times 10 to the negative 7th Tesla meters per ampere. Yeah, shooting off memory on that one. Let's see. Yeah. And again, I recommend with T and M that you put a dot in between it because the capital T means tera in prefixes. So without the dot there, that would be terameters. If you flipped it the other way, it'd be millitesla. So you need a dot. So in essence, what this does is it puts a times 10 to the negative 7th when you're dealing with SI units up front. All right, next form. If I have a vector A